Hello everybody, welcome to another video. For this one, we're going to talk about lesson 3, which is on the definition of derivative. Now, derivatives are very important. We're actually going to spend roughly half of the remainder of this class on this topic, right? Just the various applications of derivatives, all that good stuff. So to start all of that, we need to define what it is. And before we can even start on the definition of derivative, we have to revisit some old ideas. A secant line is a line that intersects the curve of the graph at 2 points. Okay, so in this example, we have the graph of the function f of x equals to x squared. And if we just go ahead and pick 2 points, say this point right here and that point right there, all we have to do is connect them together and we can find a secant line. Now, this idea is really nothing special because we know given any 2 points on the graph, we can then simply connect them as we did to create a line, right? And this line is uniquely defined by those 2 points. In fact, we can find the equation of this line by applying the slope formula, which is y2 minus y1 over x2 minus x1. And then we can use point slope form, right, to find the whole equation of this secant line. To do that, the first point we can label as x1, and then the corresponding y value, we simply plug in this x1 into f of x, so call it f of x1. Similarly, for this point, we call it x2, and we can find its y value by plugging that into the function f. So I got my 2 points this way. Once I have these two set up, then the slope of the secant line is simply y2 minus y1, right? This is your y2, and this is your y1. y2 minus y1, so f of x2 minus f of x1 all over, right? x2 minus x1, x2 minus x1. Okay, so that right there is the slope of the secant line. Now, there's actually some meaning to this. The slope of the secant line is also known as the average rate of change, and sometimes referred to as the difference quotient. The difference quotient idea is not really too exciting here. It's just a way to say that, hey, look, this is a quotient between what? Between two differences, right? Subtractions are also known as differences. So the difference quotient is really nothing that exciting here, but the average rate of change is kind of meaningful, right? It just means what happened during this interval between x1 and x2. And there's this formula is all well and good, but it loses a little bit of focus, right? Because it looks like we're given any 2 points of, on the xy plane, right, on the graph, and there's really no focus here. And there's some issue with that, mainly because we can't do any sort of algebra to kind of investigate this idea a little bit further. So what we're going to do is to relate these 2 points, right? Once we have a relationship between these 2 points, maybe we can do something about them algebraically to get more theoretical concepts, right? So what we're going to do is to relate these, and instead of working with, say, x1 comma f of x1 and say x2 f of x2, the way I'm going to do this is to focus on x1 f of x1 and relate x2 based off of x1. Okay, so instead of saying, hey, look, x2 is just some random number, I want to put x2 that's simply x1 plus h. So what I'm saying here is x2 is just h distance away from x1. So I'm relating these together, right? Kind of like Luigi is just Green Mario type of deal. So I want to relate x2 to x1 by expressing that as simply another value that's h distance away from x1. So then my formula looks like f of x1 plus h for the corresponding y value. Now the difference quotient changes a little bit, right? All I have to do is substitute f of x2 by f of x1 plus h minus f of x1 all over x1 plus h minus x1. So all I did here from the previous slope of the secant line is to simply replace x of 2 by x of 1 plus h. But now what I get is that the x1 on the bottom cancel each other out. Okay, so a lot of time you will see that the difference quotient only have a h on the bottom. That's the reason, because the x1s is going to subtract away from each other anyways. Okay, so to kind of see this this whole idea here, we have a slightly bigger graph. Let's take a look. Here we have another graph. Now this is just a zoom in graph of the x squared. You can tell the function is still the function up here is still y equals to x squared, and you can kind of zoom out a little bit, right? You can see the whole graph. This is just to zoom in to emphasize a little bit of point here. Okay, so I have this graph and I have the secant line, and the 2 points I'm choosing here is 1, 1 and 3, 9, right? Just to kind of show you what I mean earlier, we can take this and now we can then apply the points, we can then apply the formula of slope, right? So slope m is equal to, this is your y2, y1, so 9 minus 1 over x2 and x1, so 3 minus 1, and that's equal to 8 over 2, which is equal to 4. So that right there is the slope of the secant line, right? And now, of course, I can then use the point slope form. So y minus, let's go ahead and use this point because it's different for x and y. Y minus y1, so the number 9, what's your dot here, equals to, let me erase that weird looking dot there. Okay, I guess erase the whole thing. Y minus 9 equals to, so the slope is 4 times x minus 3. If we distribute the 4 and then plus the 9 on both sides, we get y equals to 4x minus 12 plus 9, and that's equal to 4x minus 3. Okay, so that is the equation of this secant line, which we actually do see. If I go back down here real quick, we do see this secant line is y equals to 4x minus 3. Okay, so nothing special here. It's just how to work with equation of lines in general. Basically, this idea allows me to find the equation of the secant line. Okay, and then this slope right here, the slope equals to 4, is the average rate of change during the period from 1 to 3. Okay. Anyways, go back to this notes here. Once we understand what the secant line is, we can then move on to what we know as the tangent line. A tangent line is a line that intersects the curve at only one point, right? At only one point. So if we're working with tangent line of, say, 1, 1, then the line intersect is just that one point right here. Okay. At this point, that line I just drew intersect with the curve of the function at exactly one point, right? So this right here is even more meaningful for us. The slope of the tangent line is now the instantaneous rate of change. And this, ladies and gents, is known as the derivative. Okay? The derivative. So how do we calculate this, right? The issue with this particular type of lines is that, unlike the secant lines, which we have 2 points. And as soon as we have 2 points, we can then apply the slope formula, right? And then the point slope formula and get the equation of the whole line. But now we only got one line. So how do we even approach this? Well, here's an idea, right? Once again, this is where limits concept comes in. If we go back to this graph over here, what I can do here is to take this red dot, right? Again, I'm focusing on the blue here. What I'm going to do is take the red dot and move it, right? And force it to be closer and closer and closer and closer, infinitely close to this blue dot. Or I can go as close as here. You can't see the numbers. It's a little hard, but it says 0.00164. Right, so very, very close to the number 1. Yeah, and I can actually go from the left side as well, right? I can go back to the left side and then kind of approach this blue side, this blue dot from the left. Okay, this one right here is 0.98175, right? So I can push the second point closer and closer to the first point. And then while I'm pushing it, I observe the slope of that purple line, right? AKA the slope of my secant line. And as I do that, I'm going to use this information to predict what's going to happen exactly when the two dots become one. This is the process of finding the slope of the tangent line. We're using the limit idea to predict how the slope of the secant line is going to change, and we're using that to predict exactly when the secant line is going to be at when the 2 points are exactly the same value. Okay, so to do that, we need to leverage the idea of limits, and this is kind of why in the previous step we need to rewrite the 2 points into a relationship of 1 point, right? This way, we can then algebraically work out some of the problems. In fact, we can already write it because previously the slope of the secant line is this difference quotient, right? F of x1 plus h minus f of x1 all over. I'll just put an h here because we know the x1 cancels out. But now, all I have to do is to make sure that the 2 points are getting closer and closer. Another way of saying that is the limit as h approaches to 0. Because remember, h is the distance between x2 and x1. So as h approaches to 0, the distance between these 2 points approaches to 0. Therefore, the 2 points are becoming 1, right? Are getting closer and closer together. Okay, so we're going to go ahead and use this definition later. In fact, for the sake of simplicity, because now we have a one value to focus on, we typically replace these two x1s with just the letter a. Okay, just for sake of simplicity. Or we can simply replace it with a variable x. Again, for the sake of simplicity. We'll get to that soon. But let's take a look at this example. This example still is this idea of using secant line to predict what's happening at the tangent line. And you're given a function here, negative 2.5 x squared plus 2, and the graph is there, right? So at x equals to 1, this is the point right here. As you plug in x equals to 1 into f, you will get that this point is 1.175. 1 comma 1.75, I should say. Okay, now the way this works, right, we're given 4 values of h, but these h just means the distance that the second point is supposed to be from the first x. So here, the very first one, when h is equal to 1, the second value is 2. It's simply 1 plus h, right? The formula is given to you here. And all you have to do here for that is you just kind of plug into the formula. So Obviously 1 plus h is 2, so you just have to plug in this value right here, and you find the average rate of change. So you just do f of 2 minus f of 1 all over 2 minus 1. And to plug that in, you just have 0 0.25, 2 squared plus 2 minus 0 0.25, 1 squared plus 2 all over 1. So 2 minus 1. Right? There should be an extra minus there. The point I'm trying to make here is that this is just something that you will punch into the calculator. In fact, the first 2 is already done for you. The answer here is negative 0.75. Okay. The ones that were left blank for us is we got to calculate the last 2 rows. So if h is 0.1, then the interval I'm working with is just 1 comma 1.1, right? It's just the first number is always 1 plus 0.1, right? The formula is again given to you here. So it's 1 comma 1.1. So the function it should be that we want to punch into the calculator is negative 0.25 1.1 squared plus 2. Maybe put a couple parentheses so I don't miss this again. Minus negative 0.25 1 squared plus 2 all over 1.1 minus 1. And if you punch this into the calculator, you are going to get negative 0.525. Of course, I did this earlier. I didn't just look at it and get the answer, okay? And I need to punch this into the calculator just like all of you guys do. So the AROC, the average rate of change here is negative 0.525. 525. Okay, let's try one more. Plug in the 0.01. That means I'm working with interval 1 comma 1.01. So the function I'm punching into the calculator is 0.25 1.01 squared plus 2 minus negative 0.25 1 squared plus 2 all over 1.01 minus 1. And again, if you punch that into the calculator correctly, you get negative 0.5025. Negative 5, oops, negative 0.5. Negative 0.5025. Okay, in fact, I did this also. You can try this out yourself. If you try 0.001 for h, the interval works on 1, 1.001, and then if you punch into the calculator, you're actually going to get negative 0.50025. Kind of a neat little pattern here, but we can see that the value, the average rate of change value, is approaching to what value? Well, it's approaching, looks like, to negative 0.5, right? As we get closer and closer to 1, so if you try 0.00001, you're going to get negative 0.50025, right? It's just going to get more zeros between the 5 and the 2.5. So it's going to get closer and closer to the value negative 0.5. Okay, so that will be my guess for the slope of the tangent line at x equals to 1. Okay. So here, real quick, why do we care about the slope of the tangent line? Well, most functions are curves, are not lines, right? We like equation of lines because it's very easy to predict what's going to happen in the future. Most functions, unfortunately, are not that predictable, so we can leverage the idea of tangent line to make predictions around the point that we're working with. Okay, so there's a lot of nice things about tangent lines, and we'll learn more applications as we progress through the class. But really, it's a very important idea. because it will tell us a lot of information about the behavior of this function locally. Okay. All right. Some notations here. If you're given a function f of x, okay. First of all, recall that f of x means x is the independent variable, right? And the output f of x is the the dependent variable. But this f of x also means the variable we're working with obviously is the variable x. Yeah, that's what independent variable basically means. So here the derivative of f of x is just f prime of x. That's the simple notation. Or the more meaningful notation is this d dx. This just means the derivative, this top d is the derivative of whatever's inside that parentheses, right? In this case, derivative of f of x, and then on the bottom part here, with respect to x. Okay, so derivative of f of x with respect to x, often known as df dx. Okay, for short. And then here in this case, we can say also that dy dx, right? If we recognize the variable y is equal to the function f of x. Okay. Last notation is just y prime. Again, we just kind of see that y is if y is equal to f of x, right? Then the derivative on the right hand side means f prime of x. So it makes sense on the left also put a prime, right, to indicate the same idea. All of these, y prime is probably the least meaningful, just because you have almost no idea what the derivative is taken in respect to, right? All of the other ones almost clearly indicates that the derivative is taken with respect to x, but y prime doesn't have that information. You have to get that information from the context of the question. Okay, that's a little bit unfortunate about things, but it should make some sense, right? Because the more simplified the notation is, I guess the less meaningful it it incorporates. Okay. So going to finally the definition of derivative. The derivative of f of x given by f prime of x is the slope of the tangent line, right? And again, we can already see this limit notation of the difference quotient. The only exception is that, of course, I replace x sub I with x, right? So now we got this formula. This is the more formal, the more precise definition of derivative. Okay, let's see an example here. Consider the function x squared minus 3x. First, find the average rate of change from x equals to 2 to x equals to 4. Well, x equals to 2 is here, so the corresponding y value is here. So we got 2 comma negative 2. X equals to 4 is here, corresponding y value is here. So 4 comma 4. Okay, so the average rate of change, again, is just your y2 minus y1 business. So go ahead and label your values. So x2, y2, x1, y1. Labeling just help you to plug in correctly. Okay, so nothing extra, nothing too difficult here. It just kind of help you to plug in numbers nicely. So the average rate of change equals to y2 minus y1, so 4 minus negative 2 all over 4 minus 2, x2 minus x1, right? And again, the labeling kind of help here because a lot of time when people see that negative, they will have it, they'll just kind of write it as like, oh yeah, it's 4 minus 2 over 4 minus 2, right? That negative tends to throw people off, is what I'm trying to say. So just go ahead and label that, especially when you're not used to doing this yet. Labeling does help. Okay. So anyways, we have this formula. All I have to do is punch it in. 4 minus -2 is 4 plus 2, which is 6. 4 minus 2, of course, is 2. So the average rate of change is 3. Okay? Average rate of change is 3. Not too difficult here. Let's take a look at the instantaneous rate of change at x equals to 4. Instantaneous rate of change, again, means the derivative, right? The derivative. So if you have a function f of x equals to x squared minus 3x, at this moment in the time, all we got are definition. So you have to start with that. F prime of x equals to limit as h approaches to 0. This is very important because that means, so if you take a look at this definition one more time, that means inside this definition, right, inside this definition here, h is the variable, not x. These x values are not variables in the perspective of this limit, right? Because inside this limit, only h is changing. Okay? Keeping that in mind, we have f of x plus h minus f of x all over h. Okay? So let's evaluate this limit by definition. Sorry, this derivative by definition. F of x plus h means whenever I see x in f of x, I replace that with x plus h. So I have x plus h squared minus 3 times x plus h. And then I minus f of x all over h. Okay? Now I clean the numerator up a little bit. Limit as h approaches to 0. X plus h squared requires FOILing. You cannot just square both of these terms. You have to FOIL. I'll leave that up to you to check. X squared plus 2xh plus h squared. And I'm going to distribute the -3, so minus 3x minus 3h, and minus f of x, I know exactly what that is too, is just x squared minus 3x all over h. Now I have limit as h approaches to 0. I can see that I have a x squared here. I have a minus x squared again. So those goes away. Similarly, I have a minus 3x and minus again minus 3x. So those is going to go away. So all I have on the top is 2xh plus h squared minus 3h all over h. And now I can see that the numerator have an h in every single term. So I can take that out as well. Equals to limit as h approaches to 0, h times 2x plus h minus 3. Right? Once I take out h from each term, I have these remaining things left all over h. And now we can definitely see that the h is going to cancel each other out. So we got h divided by h, right? This is where our limit taking techniques really kind of kick in. When we think about plugging in h, we get 0 over 0. So we're trying to simplify the limit here, right? We're trying to simplify the expression. Now that I canceled h, I got limit as h approaches to 0, 2x plus h minus 3. And finally, I can then evaluate the limit by setting h equals to 0, right, by the direct substitution method. And my result is 2x minus 3. 2x minus 3. So this right here is the derivative of my function f of x. So let me write this down. F prime of x equals to 2x minus 3. This is the derivative of f of x for any value of x in the domain of f. I'll just put in the domain. Okay, so this works for any values of x inside that domain. So the question says the instantaneous rate of change at x equals to 4. So all I have to do is plug this value into my function. So instantaneous rate of change at x equals to 4 is simply f prime of 4, which is equal to 2 times 4 minus 3, and that's equal to 8 minus 3, which is equal to 5. Okay, so the instantaneous rate of change at x equals to 4 is simply plugging in x equals to 4 into your derivative function that we just obtained, and the answer is 5. Okay, not too bad of work the first couple of times doing this limit, right? Finding the derivative as a function using the limit definition could be pretty difficult. We're going to practice that a little bit, and then I promise you things are going to get easier from here, starting from the next section. Okay, in terms of getting the basic derivatives, that is. Okay, okay, let's move on to the next one. Units of rate of change here. A lot of time we're working with actual, questions in science. We're gonna have to deal with limits or derivatives. We're gonna have to deal with units, and the derivative has units equals to the unit of the original function over the unit of x. Okay, because it is a rate of change, right? A rate of change. Rate of change is like, say, miles per hour, right? That's the rate of change. Meters per second, right? That's the rate of change. Okay, so here, for example, example number 3 here, let g of t be the distance a cheetah has traveled in miles after t hours. G of 1 represents what? Well, g prime of 1, sorry, represents the derivative of g when t is equal to 1. In other words, the derivative means the instantaneous rate of change. So g prime of 1 represents the instantaneous rate of change. Actually, let me just abbreviate this. Instantaneous rate of change in the distance at 1 hour. Okay, the instantaneous rate of change in the distance at 1 hour. So what does this mean? Well, the distance is measured in miles, right? So the unit of g prime of 1, I'll write it here. Unit of g prime of 1 is miles per hour. Oops, miles per hour. Okay, and that's really the answer to this question. Let's take a look at another example. Researchers measure blood alcohol concentration, C of T, of a man after he consumed 30 milliliters of ethanol, corresponding to 2 alcoholic drinks. Average drink during lunch. This is happening at 7 p.m. Let T represent the number of hours after consumption, which is again at 7 p.m. So you get this chart with your blood alcohol content. A is find the average rate of change concentrate between 8 to 9:30. Okay, the way you want to see this is we're starting at 7 p.m. So at 7 p.m. we are at 0 hours. So this is 0 hours. Okay, so 8 will then equal to 1 hour. Yeah, this is 1 hour. And this 9:30 will be 2.5 hours. Okay, so we're working with this one right here, and we're working with this one right here. Right, this is hours after consumption, right? Hour after 7 p.m. Therefore, right, the average rate of change is simply the C's, so CT1 minus T2, I guess, CT1 all over T2 minus T1. Okay, so according to the chart, we got 0.12 minus 0.33 all over 2.5 minus 1. Let's put 1.0 here. And that's equal to, looks like negative 0.12 all over 1.5. Negative 0.1, 0.11. What am I doing? Over 1.5. Let's take a look. Punch that into the calculator. And it looks like I get negative 1.39. Oh, wait, one. Wrong button. Wrong button there. I have negative 0.073 repeating. Okay, that's the average rate of change. Now, what does this mean? This means from 1 hour to 2.5 hour after consumption, right, my blood alcohol content is dropping by 0.73 milligram per milliliter. Okay, let me see. So blood alcohol concentration. Dropping, oops, dropping. So dropping because of that minus, right? Dropping by 0.073 milligram per milliliter per hour. Okay, so it kind of makes sense because after you drink the alcohol, your body starts to dilute it, starts to get rid of it, but at a fairly fairly slow pace here. But that's what the average rate of change means at this point. Okay, let's go ahead and take a look at this last example here. Find the derivative. Here, this one takes a little bit of algebra work here. Let's take a look. At this point, you just have the derivative by definition, so we have to use that. So here we go. F prime of x equals to limit as h approaches to 0, f of x plus h minus f of x all over h. Okay, so again, what that means here is whenever I see x in f of x, which is like right here, right, I replace that with x plus h. So this is equal to limit as h approaches to 0, f of x plus h. But that's just 4 over x plus h. Remember that entire x plus h have to be underneath the 4. Okay, one common mistake people tend to make is to write stuff like 4 over x plus h. Okay, that's not right. That's not how composition works, right? Because the x in the original function is entirely under the 4. So when you plug in x plus h, it has to be entirely under the 4 as well. Okay, once we have that settled, the original f of x is just simply 4 over x, and then all over h. Now, I'm 100% sure you've already seen something like this in your previous math classes. Uh, that's why we do these kind of things in your previous math classes. But let's take a look at how to do this kind of questions, just as a reminder. So limit as h approaches to 0. Here we're just going to add these numbers together, add these numerator fractions together. And to add fractions, I need to make common denominator. So I multiplied the one on the left by x over x, and then the one on the right by x plus h over x plus h. Okay, doing that is going to give me 4x over x times x plus h minus, I'm going to distribute the 4 here as well, so 4x plus 4h all over x times x plus h. Right, that's how I'm going to get the same denominator, but don't forget that h at the very bottom. Now I got limit as h approaches to 0. Finally, I can combine the top together, but I can see that I have a 4x minus 4x, so that goes away. But that negative also gets distributed to both of these, right? So the negative affects the 4h as well. So on the very top, I just have negative 4h, and then all over x plus h, and then all of that over h. Okay? So the next step, to help me see exactly what's happening, I think to myself, well, h is also known as h over 1. So now, when you divide it by a fraction, right, I have a fraction on the top divided by a fraction on the bottom. When you divide by a fraction, it's the same as multiplying by the reciprocal. So I have negative 4h over x times x plus h times 1 over h now. And now I can see that the h is going to cancel out. So I have limit as h approaches to 0, negative 4 on top, all over x times x plus h. And now, after the cancellation of h, I know I can plug in the h now, right? Because if I plug in h equals to 0 into here, I'm actually going to get a valid expression. So limit, oh, actually, I'm already evaluating limit at this step. I can finally stop writing this, but I got negative 4 over x times x plus 0, right? Plug in 0 equals to, h equals to 0. But that, of course, x plus h is just x, so I really have negative 4 over x squared. And I'm done. So this right here is f prime of x. Okay? Now, last question. What does the answer represent? Well, this is the instantaneous rate of change of f of x at any x value in the domain of f. Instantaneous rate of change at any value of x in the domain of f of x, right? In the domain of the original function, okay? So we always want to chase after the domain of the original function that we started with, that we started the whole example with, all right? So that's it for this video. There is a little bit of detail. There's a little bit of detail in terms of algebra and a little bit of conceptual detail. Take a look and maybe practice with homework a little bit, and I will see you guys in the next video.